Okay, so now in this video, we're going to talk about clinical reasoning, and we're going to calculate post-test probability, this time using 2x2 tables. And we're going to start with our pre-test probability, as we usually do. And then, if we get a positive test, we know that raises the probability, and we get a negative test, it's going to lower the probability of that disease. And how much it raises or lowers it depends on characteristics of the test, like the sensitivity and specificity. And so, like we talked about before, no test is perfect, and we have true positives and true negatives, false positives and false negatives. And the less of the falses we have, the higher our sensitivity and specificity are going to be. So let's take a look here. This is our 2x2 table. As you remember, we have our diseased patients in this column and our healthy in this column. And then we have our test state, which is our positive test or negative test in these rows. Okay, so we start off with a patient, and we do a history and physical, and we get a problem representation, and we compare it to an illness script like we talked about before. And based on that, we come up with a probability of disease. The greater the match of the illness script to the patient, to the problem representation, the higher the probability, and vice versa. The lesser the match, the lower the probability. But in this case, let's say it came out to about 45, okay? And so now we have a pretest probability of 45%, meaning we have a 45% chance that we think that this person has the disease. So let's say that there are 1,000 patients exactly like this one, right? And 45% of them are going to have the disease. That means we have 450 in the diseased state column, and 550, the rest of them are going to be healthy. And so now we can fill in the rest of the table if we get some more information. So let's take the test characteristics. So sensitivity. And if we remember, sensitivity is going to be the number of people with, of all the people who have the disease, how many of them have a positive test. So it's going to be this over this whole column. And so we know that 75% of the people who are diseased are going to have a positive test. So we could take 75% of 450. And we get 338, or we could just solve for x. And we know that this column has to add up to 450, so 450 minus 338 equals 112. Now we can do the same thing with the specificity in the other column, right? Specificity says of all those people who are healthy, how many of them have a negative test? And we know it's 66%. So 60% of 550 equals 363. Or we could solve for y, right, from the specificity formula. And again, we know that this has to add up to 550. So we subtract 550 minus 363, and we get 187. Great, we're almost done filling out this table. Now we have to say, what is the total number of people that had a positive test? Well, we have our true positives and our false positives. We can add those up when we get that there. And then we can figure out our total number of negatives, right? So 112 plus 363, so our true negatives and our false negatives, and we get that 475. So 525 was the total number of people with a positive test there. Okay, now what do we want to know? What we really want to know is of all the people, let's say the test was positive, okay? Of all the people with a positive test, how many of them actually had the disease? And how can we figure out that number? That is something we know already. That's our positive predictive value, right? If the test is positive, how well does it predict that someone has the disease? And so we can calculate that, right? Given a positive test, what is the probability of disease? Well, it's 338 over everybody with the positive test. So 338 over 525 is 64%. So given our initial condition, of saying we had a 45% pretest probability, and these test characteristics and a positive test, now we think that we've increased our probability to 64%. We could do the same thing with negative as well, right? Given a negative test, how likely is it that the patient that we have doesn't have the disease, right? Like, how predictive is a negative test in saying that someone doesn't have the disease? So we do the same thing. We do 363, which is doesn't have the disease, over everyone with a negative test, which is 475, and so 76%. So 76% of the people with a negative test are not going to have the disease, given this 45% pretest probability. So with this pretest probability of 45%, if we have a positive test, our probability is going to jump up to 64%. If we have a negative test, it's going to jump down to 34, subtracting that. And so you're thinking, wait, I'm not going to do all this math when I see every patient, and none of us do. This is not something that we do. We don't do this math in our head. There's another way to do this, right? And we can take something called likelihood ratios, and what they do is they kind of, the way we're going to do it is going to take the sensitivity and the specificity and the odds and blend it all together into these likelihood ratios. And you're going to get a likelihood ratio for when a test is positive, or the positive likelihood ratio, and a likelihood ratio for when the test is negative, or the negative likelihood ratio. There are formulas that allow you to calculate this, but we're not going to go over that. Just go find something on a website that'll do it for you. So I plugged in those numbers, 75 and 66, and you can see here I got a positive likelihood ratio of 2.21 there, and a negative likelihood ratio of 0.38. So what do we do with these numbers? Now we need something called a Fagin nomogram, and let me take you through this. So this one has all the pretest probability along it, and you can see it goes from 0.1 all the way to 99%. And it doesn't follow a standard linear scale. It looks like it's logarithmic, right? So 0.1 to 0.2 is this big here, but then we go to 0.5, 1, 2, 5, 10. So you can see it follows this logarithmic scale here, all right? But it's still probability. Post-test probabilities are on this end, and they're flipped upside down. So 0.1 is at the bottom, 99 is at the top. And you can see we don't have a 0 and we don't have 100% because we can never have certainty in medicine, all right? And then what we do is we plot points on here. So if we had a 10% pretest probability and a likelihood ratio of 2.21, we draw a line. It's going from 10% through 2.21 all the way over here, and we see that's going to bump our probability up to our post-test probability to maybe around 29%. What if we had a pretest probability of 30%? Then what? Well, we go through here and we go through the same number here, 2.21 on the likelihood ratio line, and we follow that line all the way through, and now we're at about maybe 59% or 60%. And so that's a way to kind of calculate post-test probabilities pretty quickly using likelihood ratios. We can do the same thing with the negative ones, right? So let's take that same 10% probability we had, and we had a negative test, and our negative likelihood ratio was 0.38, so that's somewhere around there. So we draw a line through these and continue it all the way across, and now our probability, post-test probability, goes down to 2%. We went from 10% to 2% with a negative test, in this test with a negative likelihood ratio of 0.38. Let's take that same one, 30%, right? So what happens with 30%? You go from 30% through here, and you end up somewhere around, let's say, 7%. And so we decreased with the negative test from 30 to 7. And so you can see how likelihood ratios work. Now, even this we're not going to necessarily pull out a Fagin nomogram with every patient that we see, but we can think about a test and say, well, what is the likelihood ratio of this? If the likelihood ratio is pretty high, it's going to raise my probability pretty high, and we'll just estimate in our head. Like, I think this person it's pretty likely. We had those probabilities before of likely, very likely, unlikely, very unlikely, and uncertain. Let's say we were around 50%, or we were in that likely column, and we had a very high likelihood ratio positive. Then we say a positive test there is going to really jump us up into the very likely. And maybe we had a likelihood ratio negative that was very low, right? Maybe it was like 0.05, right? So that's a pretty low one. So 0.05 would be there. So that's going to, we know, drop it down quite a bit as well. So we can kind of make these estimates in our head. But you should know where those estimates are coming from, and this is what this Fagin nomogram does, and the likelihood ratios. And so thank you very much for watching. This kind of concludes how we're making our diagnoses, and we're going to have one more video, I think, that's going to be a summary. All right? Thank you for watching.